So in your math class, you probably come across something called the distance formula. And your teacher gives you this nice long formula that has a radical, and we even have an x1 and x2. We have some squareds in there. And it's this nice long formula where you have to take a difference, you have to square numbers, you have to add them, and then take a square root. And sometimes it even comes out to be a whole number, or we're left with a radical. Now, what if we didn't want to use that formula? What if there was something else we use all the time, in notably geometry, that would help us do that? So let's take a look. So right here I have two lines, or I have a line here from 2 points. I have A and B. If I connect those two, let's get a black line here, in a way that I make a triangle straight across from A, a horizontal line, drop down a vertical line from B, I make a right triangle. So really, we have this line here from A to B, which is the hypotenuse of a right triangle, or right hypotenuse. And then I have these two other lines from A and B, the ones that meet at the right angle, which we could almost call legs, because it is a right triangle. Now, if only we had something in geometry that uses the hypotenuse in each of the legs. Well, we do, and that's probably our most popular theorem, the Pythagorean theorem. And that is the hypotenuse squared is equal to the sum of the lengths of the legs squared. That's really what we can use for the distance formula. I have a graph, I can draw a triangle. Now, you may be looking at it and go, but I don't have numbers, it's just a triangle, I can't just draw things. Well, alright, let's go back down and look at our triangle. If I count that bottom leg, that leg that goes from A, it takes up 8 boxes. The vertical leg, the one that drops down from B, takes up 6 boxes. So we could come over and we could say that AB squared is equal to 8 squared plus 6 squared. And then we get that AB squared is equal to 64 plus 36. We come out with 100, and hopefully you recognize that when you have AB squared equals 100, AB is 10. So if I would have done the distance formula, I'd get the same answer here. That doesn't change it. But now I don't have to stick to that formula. I can just remember it's Pythagorean theorem. So let's look at a couple quick ones. Maybe these are points on a graph, where I have x and y coordinates for each of them and the points. I can almost ignore that fact and just come in and draw in some triangles. So C to D, I have a leg of 3 and a leg of 4. It goes down 3 to get from C to D, but that's okay. It's still 3 units tall. So I could say that my hypotenuse, let's call it x here, x squared is equal to 3 squared plus 4 squared. X squared equals 9 plus 16. X squared equals 25, which we should hopefully know means x is 5. So the length of my hypotenuse there is 5. Let's go over to E and F. Drop this down, make a triangle. My two legs are going to be 3 and 3. So now my hypotenuse, we'll use a little better notation here. We'll call it EF because it is a segment. We're looking at the segment length. EF squared is equal to 3 squared plus 3 squared. EF squared is equal to 9 plus 9, which comes out to be 18. Now all this comes out to be is that EF is equal to the square root of 18, which simplifies, because 18 is 2 times 9, to be 3 root 2. Now, give yourself an extra credit point here, wherever that may apply. If you said, hey, wait a minute, I know that's 3 root 2 because that's a 45, 45, 90 triangle, and the hypotenuse is root 2 times the leg. All right, we come down here. We're looking at GH. Let's draw on our triangle. We go up 3. We go over 5. So GH squared is equal to 3 squared plus 5 squared. GH squared is equal to 9 plus 25. This comes out to be 34, or square root of 34 is GH. h. Well, 34 is 2 times 17. Those are both prime numbers. I can't factor it down anymore. I don't have any perfect squares from that, so I'm just going to say that gh is the square root of 34. Now we could probably say units here if we were being approximate or being exact and having our units. And we can guess what that's going to be because I know that the square root of 36 would be 6 and the square root of 25 would be 5. So I know that's between 5 and 6, probably a little closer to 6, but we want to just say the square root of 34. Last one, I and j. We have 2 and 5. So let's think about this. We have gh and ij. Each of them have a leg of 5, but one of them has 3, the other has 2. So what do you think? Do you think that gh or ij is going to be longer? Well, if we come in and write ij squared is equal to 2 squared plus 5 squared, ij squared equals 4 plus 25, we get the square root of 29 is equal to ij. Square root of 29, that's a prime number. We're going to leave that as a root 29. We should write units there, and that one turns out to be smaller because, yes, that one's still between 5 and 6, but it's going to be a little bit closer to 5 because 29 is closer to 25 than 36. So there we go. We just solved and found the distance between 2 points without using the distance formula. That doesn't mean we don't have to know the distance formula. You're not getting off that easy. But sometimes when we have points on a graph, it's just easier to use good old Pythagorean theorem. Hope this video helped. If you got another question, go to my website and submit one, and maybe I can make a video from your question.